Hey guys, you're watching Python tutorial videos on my YouTube channel Python for Microscopists. In the last 5 videos, we learned a little bit about units and why they're good for image segmentation. And we also learned why they're called unit. So if you haven't watched those videos, please go ahead and have a look at them. And we, of course, also put together a bit of code to define the unit using chars in Python. And we also looked at the data that we are trying to analyze, which is nothing but a bunch of cells that we are trying to segment against a given background. And in this tutorial, let's go ahead and execute this code, run the code, and look at the results and see if we can make any sense out of it. Okay, so before jumping in, again, let's have a look at the unit that we coded in Python. So here is the structure. Always write down exactly, what you're trying to code beforehand, so you get a very good visual. So here our input images need to be resized, all the images to 128 by 128 by 3, and then goes through a couple of convolutional layers here, and then it goes through this max pooling operation, and then a couple of convolutional layers, max pooling, convolutional, max pooling, convolutional, and then go back up and then do the upsampling, and hence this is called unit. Okay, and as we are going up, we are going to concatenate these two, one from the down path or the encoder path and the upsampling path together, and apparently this operation actually is the reason why we get this spatial information when we are trying to do this segmentation. Okay, so this is what we have actually coded in our Spider IDE. And again, just a quick recap of the code here. We started by importing the libraries that we need, and then we defined our image width, height, and number of channels as 128, 128 by 3. This is exactly what we want, for our input layer. And then we looked at our data. Again, I think it's worth going through this again. So there are two folders, one called stage 1 train and the other one called stage 1 test. Okay, and again, I got this data from the source I mentioned about in my previous tutorial. So let's not go into those details. And this is again directly from the Kaggle 2018 competition. Okay, so these are a bunch of cells. So in stage 1 train, each image is represented by a folder, and within a given folder we should have two subfolders, one for the actual image itself, and the other folder contains a whole bunch of masks corresponding to each cell that's represented in these images. For example, if I open this images right there, let me drag the screen from my other side. So there you go. So this obviously is a color image, and there are a bunch of cells, and someone painted the pixels for each of these. And under masks, you can see a whole bunch of images. So in this folder, I have 70 images. So which means in this image, there are 70 different cells that are identified. But unfortunately, each cell is represented or identified in a different image, which means one of the operations we need to do to get our data ready is to merge all of these images into one single mask image where all the cells are kind of represented in that one image. Okay, which we did in the code. So if I randomly select another image right down here, again, same thing, images and masks. Under images, this is now a black and white image, or a grayscale image, I should say. There you go. Here is how the image looks like. Looks like there are probably 10 or so cells. So if I go to masks, you can see there seems to be about 8 cells that are labeled in this specific image. So this is how our data is structured, and inside the stage 1 test folder, very similar. Okay, we have some names, and you go into that folder. Obviously, these are test images, which means we do not have corresponding masks for these images. These are just test images. So within each of these, I have an image. Images folder with a file name same as the parent folder name, except with an extension of PNG. These are all PNG files. So this is our goal is to build a unit, train it using these training images, and then test them. Okay, so that's exactly what the code does. So initially we said, okay, our training path is stage one underscore train, testing path is stage one test, and then we just generated some random seed, so our results do not vary every time we actually run. Because the same seed is used wherever the random numbers are used within this within our code. Okay, and then we created empty arrays for our X train and Y train data sets, and these are the arrays that gets filled as we are resizing these images later on. That's pretty much it. Okay, resizing of training images is, again, we are going through this path, which is our training path plus whatever that ID name is, and again the ID name is nothing but this name, right? So that's the ID name that we are extracting up here, and then walk through this images folder. In this case, we should have only one image with an extension PNG. We are reading that, assigning that to the image variable, and then we are resizing it to 128 by 128. And we are doing pretty much the same for mask, except for mask, we have to do a bit more because within each masks folder, we have a whole bunch of images representing each cell. Okay, so all we're doing here is merging all of those, and np.maximum is nothing but we are actually looking at, okay, at a given pixel, select the maximum value, which is obviously wherever there is a cell represented, that's the value we are going to pick. Okay, so we did that. We did pretty much the same for the test images, except we don't have mask in the test image, so it's just the first operation there, and then we are done. We then looked at picked a couple of random images or one random image here just to make sure, okay, is everything looking fine? Now I commented that because everything was looking fine, so we don't need to run that piece of the code. The meat of this is building the unit model here. So this is the key part. And in fact, I should say this is probably the easiest part of this entire code. The toughest part was this part where you have to figure out, based on your input data, how does the input, how to handle these input images and how to structure them. In fact, you would spend 80% or more of your time trying to get things ready rather than actually doing the real machine learning or deep learning stuff. Anyway, so our input layer is nothing but a layer with a 128 by 128 by 3. And I converted that using a lambda function. I divided every pixel value by 255 to convert my 8-bit integer or into a floating point value, because the KRS layers, convolutional layers, and everything else are going to deal with floating point numbers. In fact, the weights are all floating point numbers anyway, so when you multiply this by the weights, it's going to convert into floating point anyway. But when I ran this code initially, it said, okay, it needs a floating value. That's why I kind of divided every pixel value by 255. Anyway, and then we put together these various layers that actually represent the unit that we are trying to build. And once you run this code, this part of this code, it actually prints out the model summary. And again, a sanity check before you do anything. First, construct this. Look at the model summary and make sure it matches what the goal is here. Okay, which we already did. So let's just go through, and then we defined a few checkpointers. Checkpointer is, again, if something goes wrong, okay, I have a model that got saved at that point. So in this case, we said, okay, save models every time after every epoch and save the best only. So if the next epoch the model is better, then it's going to save that one. Okay, you can also save the weights only, and so on, but we chose to save the best model only. And then we also included early stopping criteria, where we said, okay, monitor the validation loss parameter. And if that doesn't get better, then go ahead and stop. And the patience equals to 3, which means it actually goes 3 epochs further to make sure that, okay, that stop point is really the best stop point. And we also created another callback for Tensorboard. This is where we can graphically look at various things, and those things or parameters are stored in a log directory called logs. Okay, and model.fit. So we take this model and we are fitting it to the X train and Y train data. And this is nothing but the the pixel values that we are actually getting by reading the images up there. So where are we? Okay, so X train and Y train, and we are holding out 10% of the data for validation, and we are running this in the batch sizes of 16, and for how long? 100 epochs. Well, it probably doesn't go all 100 epochs because we have this early stopping criteria. So probably it stops after 20, 25. I don't know. We'll have to see. And the callbacks that we are using is these callbacks. And I added a little bit of code down here to actually, okay, once it's done, take that model and then predict that on some random images that we are going to select. Again, here is the random number that gets generated, and we randomly pick an image in among 600 or so images that we have, and it's going to predict, from training and validation data set and testing data set. And at every pixel, the result from this deep learning from UNet is going to be almost like a probability value, right? So the value would be anywhere between 0 to 1. So I want to convert that into a thresholded value. So I actually said, okay, any value above 0.5 at a given pixel, okay, assign that as prids underscore train underscore t. This is basically, I'm just doing some thresholding right here by setting a hard limit as 0.5. Anything above zero point 0.5, I'm confident that pixel to call it as a cell. If it's below that, then it is not a cell, it's the background. Okay, that's exactly what we are trying to do here, and then visualizing down here. Okay, so now let's go ahead and hit the run button. And before I do that, let me open my task manager so we can actually have a look at exactly how the resources are being used. So let me go ahead and bring this here. So right now everything is very quiet. Okay, so let me go ahead and hit the run up there, and now you should see something happening. The first thing it does is, of course, resize all the images. This is a little bit of a slow process, and it is going to use CPU only for that purpose. And by the way, I should have mentioned I'm using a laptop actually with an NVIDIA Quadro GPU, and I installed TensorFlow GPU, and that's all I needed to do. There is nothing else I need to do here to tell the system to use GPU. Of course, you can write additional lines of code to actually say, okay, don't use full GPU, use only 30% of the GPU or so. But for now, I'm just going to leave it as is. So this line, import TensorFlow STF, is going to basically take care of it. If there is a valid GPU like NVIDIA, for example, it's going to use it. If not, it's not. Again, watch my video about how to install or invoke GPU for deep learning. Okay, so once this part is done, now you can see that it's actually printing our model summary. And now it should actually start. Let me actually bring up GPU. So it's actually ramping up GPU. As you can see, I have only 2 GB, which is still better than not having a GPU. So you can see it's actually going pretty fast, as you can see. Yeah. So epoch 1, if this were only on a CPU, that would be painfully slow. So I definitely recommend getting a compatible GPU to accelerate your computation. So let's wait until, I hope it doesn't go all 100 epochs, but let's keep an eye on the screen. I'm going to speed up this part of the video so we don't stare at the screen while it's doing this part. So here you go. So it actually stopped before 100 epochs. So let's go back up and see when it actually stopped. So this happened after, if I can see it, epoch 20 actually, right there. Okay, so you can see the validation accuracy 0.968995. It's getting better. but then 93, 96, 9675. Okay, so and now it's actually printing a few of these images down here. So here is one, and here is the segmented image, and here is the thresholded image, and here is another image, segmented and thresholded. Okay, of course it can be better, and again, many ways to make it better, change some of these parameters. But now the most important thing, let's actually see how visualize this model. Okay, so because we used our Tensorboard as one of our callbacks, we can actually visualize these on Tensorboard, which I think is pretty cool. So this is how you can do it. I mean, first of all, you can look at online documentation on how to load this Tensorboard. On Windows systems, it can be very tricky. Most of the recommendations online for some reason didn't work for me, and I'm going to show you what worked for me. Okay, so running the Tensorboard or a command from the Windows command prompt actually is what's recommended online, but you can run the Windows command prompts right from the kernel right here by putting an exclamation mark first, and then tensor board. Okay, and then give the log directory, the location of the log directory, and our log directory is in this case logs. Okay, it's in the same folder uh, under a subfolder called logs. And now we have to define the host because we are trying to open this in a browser. Okay, so use local host. Okay, and which port? I'm gonna just say 088. Okay, so now when we open this in a browser, we just need to open that port 80 localhost 8088. Okay, so let's go ahead and run this. So I just hit return. So now I can open the browser. Okay, let me bring my browser to this screen, and I just need to type. Let's actually go ahead and type HTTP localhost. Okay, and this is 8088 right there. Okay, so here you go. This is the Tensorboard, and now you can go ahead and look at this. This is a bit busy. Again, I'm still trying to get myself familiar with Tensorboard. How can I only look at like one how should I say, a much cleaner version of this epoch accuracy and also epoch loss. But in general, let's actually try to follow this. You see how, let's turn the validation off to begin with. Only look at this training. So for training, you can see it slowly increased and then it almost saturated right there. Okay, so initially we gain a lot of epoch accuracy as you go, initial training, and then after it kind of flattened out. Okay, and same with epoch loss. Okay, it's flattening out. And if I turn the validation on, as you can see, it's kind of following the training, and same thing, it's following the training even for epoch loss. Again, I should apologize for this busy screen. I don't know how to clean it. I don't want to do it on this video right now. In fact, I should say this is probably the second time I'm opening Tensorboard and to see. Again, if you're a researcher trying to find out how to change certain parameters to make your unit better, obviously you'll be spending a lot more time here trying to understand what's going on. Another cool thing is that if you go to graphs, it actually this is the model that we just created. Okay, you can visualize this model right there. You see how now if I actually double click somewhere, in fact I can zoom in. Double clicking opens this. At this point, it's actually concatenating. It's doing some other operations. In fact, let's actually go convolutional 2D at this node right there. So here it's doing convolutional 2D, and then it's adding some bias and ReLU and identity. And if you zoom in, you can see the dimensions that are actually passing through and all of that. So this is a great way of visualizing your unit. And also looking at some, I can expand this bias add. It gives me even more information. On the right hand side, you can see much more information right there. Okay, again, my intention is not to go through this Tensorboard in this tutorial because first of all, I'm not qualified to do that yet. Maybe I'll teach myself what's going on here and then create another video later on. But the intention is to show you that, okay, you can create this tensor board. You can come here. You can look at the scalar values, which is whatever the parameters that you're monitoring. In this case, epoch accuracy, epoch loss. You can add more of these parameters that you would like to monitor. And also you can look at the graphs here. Okay. So I hope you found the series of tutorials about UNet very useful. And again, please try to work on your own data sets. And to me, frankly, the biggest challenge with this unit is not building this network, because this is the easiest part. The biggest challenge is getting the data ready. Try to figure out how to handle your data. I wish I had my masks all in one image. I mean, rather than a whole bunch of images. So I have my own way of treating this. But anyway, it's up to you how you want to deal with your housekeeping when it comes to handling the files and everything else. So hopefully this provides a good background for you to get started. So please subscribe to my channel for more such content, and keep encouraging me to create more such videos. And in the next tutorial, I'll introduce a different topic. But until then, please subscribe. Thank you very much.